So today we are going to kick things off with analyzing a steady state sinusoidal circuit in the time domain. And I believe I have mentioned this before, but I will mention it again. This is not the way that we are going to actually do things. I want to show you how wildly difficult this is, and then introduce how we will work in the frequency domain and how much easier it is as a reason to convince you never, ever, 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 ever analyze these circuits in the time domain. Okay. So the circuit that we're going to be looking at seems like it should be incredibly simple to analyze, right? So I'm going to have some voltage source, Vs of t, connected in parallel to some resistance, 10 ohms. And then over here on the right-hand side, I'm going to have a capacitance that will be 5 millifarads. All I want us to figure out is this current Is of t that is leaving the positive polarity terminal of our voltage source if Vs of t is equal to 12 cosine 5t plus 10 degrees volts. Now, before we start our analysis here, I want to talk very briefly about a concept called force response, which we actually talked about a little bit at the end of transient analysis, right? So when we were dealing with our transient analysis problems, we saw that our force response was what was going on at t is equal to infinity. And so if we had a DC excitation function in our system, meaning a DC source in our system, we saw that our system, after the transient condition was over, still had either a DC voltage or a DC current. Well, in this system, we're starting with a sinusoidal signal. So I would argue that if we start with a sinusoidal signal, our response should also be a sinusoidal signal. So I am going to guess that Is of t will be of the form Im cosine 5t plus some phase angle theta I amps. That's what I expect my result to be, because if I put a sinusoidal signal in, I should expect to get a sinusoidal signal out of my system. Okay. So with that in mind, I'm going to approach this problem by using Kirchhoff's current law. So I'm going to say that this current flowing down through the resistor is IR of t. This current flowing down through the capacitor is IC of t. And applying Kirchhoff's current law, we find that Is of t is simply IR plus IC. Now, since all of these elements are connected in parallel, they all have the same voltage drop over them. And so we could express IR of t as Vs of t divided by R. And we could express IC of t as C multiplied by the derivative of Vs with respect to time. Okay. So doing this math out explicitly, IR is equal to Vs divided by R is going to be 12 cosine 5t plus 10 degrees volts divided by 10 ohms gives us 1.2 cosine 5t plus 10 degrees amps. just Ohm's law. IC of t is C times the derivative of Vs with respect to time. So C is 5 millifarads, so that's 5 times 10 to the minus 3. A farad is an amp second per volt. When I take the derivative of a cosine function, my omega is going to come out. Sorry, so I'm going to have 5 per second. And then over here, I'm going to have negative 12 sine of 5t plus 10 degrees. Let's see, that should be volts. Looking at our units here, this volt cancels this volt. I have seconds multiplied by per seconds, so I'm left with simply current measured in amps. And I'm going to have to throw this into my calculator because I accidentally wrote something down wrong and I don't want to correct it. 5 times 10 to the minus 3 times 5 times negative 12 gives me 0.3 negative 0.3 sine of 5t plus 10 degrees amps. So circling back around, this means that IS of t is 1.2 cosine 5t plus 10 degrees minus 0.3 sine 5t plus 10 degrees amps. So this wasn't particularly difficult. That being said, is the form that we got for IS of t of the same form as we would expect? Not really, okay? So what I mean by that specifically is what we determined, we have a combination of sinusoidal functions instead of a single sinusoidal function. So what I want to do is I want to throw these expressions into Desmos really quickly, so that we can see what happens when we combine these sinusoidal functions and if it's going to come out looking like something useful. Okay. So our first term was 1.2 times the cosine of 5x plus 10 degrees, and I'm going to multiply this by pi over 180 so that I'm consistently using angles and radians. And then we had negative 0.3. Actually, let me go up here really quickly and call this IR. There we go. And I'm going to do the same thing here really quickly. This is just going to be I. Oh, goodness. I'm so used to MathCAD, I'm consistently making the screen smaller and smaller and smaller. Don't want that there. All right. Dang it. How? Let's see. Sorry, I'm trying to remember what the right keystroke is to get that subscript because apparently I just accidentally fell into it a second ago. Shift what? Shift minus, there we go. Not control like in MathCAD, thank you. IC is negative 0.3 times sine of 5x plus 10 times pi over 180. And so this last thing I'm going to do is I'm just going to add these two together, right? So IR plus IC. And if I turn off the green and the red, I see that this is a simple pure sinusoidal function, right? So combining those two things together should be able to be expressed as a single sinusoid having some particular magnitude and phase angle. So now what we're going to do is we're going to go back and we are going to suffer through trig identities to try to make that happen. Oh, boo hiss. So (1.2) cosine of 5t plus 10 degrees can be written as 1.2 times the cosine of 5t times the cosine of 10 degrees minus the sine of 5t times the sine of 10 degrees. And then we're going to have down here, this is still the same line of math, 0.3. So this would be sine of 5t cosine 10 degrees plus cosine 5t sine of 10 degrees. And this whole thing is expressed in amps. That's using two of the trig identities that I gave you guys in our last class meeting. Well, cosine of 10 degrees and sine of 10 degrees are just numbers, right? So what we can do is kind of move things around a little bit here, right? So for instance, my cosine of 5t, if I pull that part out, I can see that I'm going to have a 1.2 times cosine of 10 degrees term. And then I'm also going to have a minus 0.3 times sine of 10 degrees term. Now I'm pulling out my sine of 5t. And for that, I'm going to have a negative 1.2 times sine of 10 degrees. And then I am going to have a negative 0.3 cosine of 10 degrees. Have I done my algebra correctly here? Pulling things out and lumping together my terms. So if I make a mistake here, obviously the answer is going to come out wildly incorrect. So let me just double check the signs on thing again, right? So this 1.2 cosine 10 degrees is coming from this part and this part. This negative 0.3 sine 10 degrees is coming from this part and this part. This term of negative 1.2 sine 10 degrees is coming from this part and this part, and the negative sign is because of that negative sign there. And let's do purple here. This negative 0.3 is coming from this guy and this guy right here. So I think I've done all of that correctly. So now we can simply put 1.2 cosine of 10 degrees minus 0.3 sine of 10 degrees in our calculator. And I get 1.1296. So let's call that 1.130 cosine 5t. Now I'm going to do negative sine of 10, negative 1.2 sine of 10 minus 0.3 cosine of 10. That comes out to be negative 0.504. Sine of 5t. So at this step, and I'm going to put a box around this because we're actually going to come back to this guy. We still have a combination of sinusoidal signals, but at least we don't have a phase angle. So arguably it's a little neater, but it's still not exactly where we want things. So the form that I am expecting, just to reiterate, I want some magnitude Im cosine omega t, which in this case, omega is just 5 radians per second, plus some phase angle theta I. If we used one of our trig identities, we could say that this would be Im times cosine 5t cosine theta I minus Im sine 5t sine theta I. From this realization, I can see that 1.130 must equal to Im times the cosine of theta I, and 0.504 must be equal to Im times the sine of theta I. So now, using the trig identity that Im cosine theta I squared plus Im sine theta I squared will be equal to Im squared times cosine squared theta I plus Im squared times sine squared theta I is just equal to Im squared. We can see that our magnitude Im is going to be the square root of 1.130 squared plus 0.504 squared. Are you all following that derivation, just to be clear here? Anything seem? So throwing this into my calculator, I have the square root of 1.130 squared plus 0.504 squared, and I get a peak value or magnitude of 1.237. To find my phase angle, I know that my phase angle theta I can be found as the Actually, let me do it this other way. So tangent of theta I is simply sine of theta I divided by cosine of theta I. That's the definition of a tangent function, right? Does it hurt anything if I multiply the numerator and the denominator by IM? Not at all. They cancel each other out, right? So from this, my phase angle is just going to be the inverse tangent of 0.504 divided by 1.130. That's 0.504 divided by 1.130. And I wind up getting a phase angle of 24.038 degrees with a little bit of rounding error. Putting this together, I can say that IS of t is then 1.237 cosine of 5t plus 24.038 degrees amps. I'm going to put a box around this guy as well. So now, let's go back to Desmos and let's make sure that we did this correctly. So 1.237 times cosine of 5x plus 24.038 times pi over 180 the black curve has completely overlapped purple curve, which means those two things are identical to each other. So that is one way to work a problem like this. Now, the problem that we just worked is literally a voltage source in parallel with a resistor in parallel with a capacitor. It's not going to get much easier than that, and that took me 25 minutes. Okay. Doing it in the time domain, doing our analysis in the time domain, if we had even one more component in there, would add probably another 20 minutes of complexity to this problem. So something that we're not particularly keen on doing. Okay. So I want us to approach this from a slightly different perspective. Okay. Let's go back towards the beginning here. Our sinusoidal function carries the exact same information as a complex number does, right? So what I'm going to do is I'm going to represent this 1.2 cosine of 5t plus 10 degrees as the complex number 1.2 angle 10 degrees. And then I'm going to have minus 0.3 angle negative 80 degrees. The reason I'm choosing negative 80 degrees is because I have converted my sine function into a cosine function by subtracting 90 degrees from the phase angle. So I would like you all to put this number or put this mathematical operation into your calculator and tell me what you get in both polar form and rectangular form, please. Anybody got some results for me? So in polar form, 1.236,9, so 1.237, with an angle of 24.036 degrees. Which, if I'm not mistaken, is literally the exact same magnitude and phase angle that we got a moment ago, right? What about rectangular form? One 1.1296, so 1.130. 0.504J, which happens to be the exact same numbers that we got at this stage that I highlighted in yellow, except that the sign on the imaginary term is incorrect. And the sign on the imaginary term is quote unquote incorrect because of that trig identity. Cosine angle 1 plus angle 2 is equal to blah, blah, blah minus the other thing, right? So realistically, if we want to do any mathematical operations involving trig functions, we can do them using complex numbers and get the same result much, much easier, okay? So that is why we work using complex numbers to solve these problems. So just as a quick heads up, let's take a look at some of your web work stuff or homework set number 19. Let's look at problem 1 here really quickly. So this is the leading and lagging stuff. We covered that in class on Wednesday. This guy right here, this is a prime example of something that if we did this out by hand, it would take us 25 minutes or more. Doing it using complex numbers is rather trivial, okay? So how would I represent that first term, 50 cosine 100t minus 163 degrees as a complex number? $50 angle negative 163, all right? And then to that, I'm going to subtract. So how do I represent that 15 sine 100t plus 114 degrees? So the magnitude is going to stay the same. We're going to have 15 angle, and then I subtract 90 degrees from 114, which I believe should give me 24 degrees. And I get 64.914 with an angle of negative 161.386. I'm going to change that to rectangular form, where I got negative 61.518. And then I had negative 20.719J. So I'm going to put in positive 20.7196. So let's call that 720 because I have to remember to change the sign on my imaginary part to put it in this form. And let us check our answers. Boom. Everything correct without doing any trig identities. Well, I take that back. We did have to use that one trig identity and convert our sine function into a cosine function, right? So complex numbers is the way to do trigonometric math all of the time. So now let's talk about why that works. So I'm going to explain why this works for circuits using superposition. So let's say that we have black box network. Over here on the left-hand side is my input signal. I'm going to call this X1 of t. And over here on the right-hand side is my output signal, Y1 of t. The example problem that we just worked, we showed that for an input signal of the form xm cosine omega t plus some phase angle theta x, we got out an output of the form ym cosine omega t plus theta y. That is literally what we just proved with our example problem. Okay, we put in a sinusoidal input signal, we get out a sinusoidal output signal. Let's take that same black box network. We're going to apply a slightly different input signal, which I'm going to call X2 of t. And we should be able to observe slightly different output signal, Y2 of t. So let's say in this case that X2 of t is equal to X sub m, sine omega t plus some phase angle theta x. What would we expect the form of Y2 of t to be? Anybody have any thoughts? Yeah, so if we put a sine function, if we put a cosine function in, we got a cosine function out. If we put a sine function in, we should probably get a sine function out. And this should be very easy to deal with, since we know that cosine functions and sine functions are literally the exact same thing. They're just time-shifted versions of each other. All right, so now, how many of you remember the homogeneity or scaling property of superposition? So the scaling property of superposition said that if we scale our input signal by an arbitrary factor, our output should scale by the exact same factor. Well, I'm going to scale this signal by j, which means my output should scale by j as well. Looking at this one last time, if I apply an input signal x of t and measure my expected output signal y of t, let's say that this time x of t is x1 plus x2, right? So we're using the additivity property now. So if I have xm cosine omega t plus theta x plus xm sine omega t plus theta x, this is going to be jxm sine, etc. my expected output would be Ym cosine omega t plus theta y plus j Ym sine omega t plus theta y. Well, according to Euler's identity, my input signal is really just xm e to the j omega t plus theta x, which is the exact complex number that we put in, right? So what's really, really interesting about this is that the real portion of our input gives us the real portion of our output, and the imaginary portion of our input gives us the imaginary portion of our output. There is no mixing of anything. So that means that if we were to excite our circuit with a complex number, the real portion of which is the time domain signal we're interested in, the real portion of our output would be the exact time domain response we were trying to find. That's why we get to use complex numbers to analyze circuits, because the real portion, which is just the cosine function we input in, gives us the real portion of the output, which is just the time domain response that we're looking for. So electrical engineers have come up with a slightly even lazier way of doing things. Okay. Yes. So we choose to represent our complex number excitation using what's called a phasor. Okay. So let's say that we have a voltage signal V of t and a current signal I of t. Our voltage time domain representation would just be of the form Vm cosine omega t plus some phase angle theta v. And our current waveform would be of the form Im cosine omega t plus I. And as I mentioned a moment ago, these are our time domain signals. Each of these signals is simply the real part of the following complex numbers: Vm e to the j omega t plus theta v, and Im e to the j omega t plus theta I. I'm going to call this a mixed domain signal because it's kind of in between the time domain and the frequency domain. So it's a complex number representation. Okay. Our last representation we're going to do, and this is what electrical engineers invented, is what's called a phasor. Okay. And so a phasor is just a way to represent this signal as a complex number. Okay. So my voltage phasor is simply going to be the magnitude of my voltage with a phase angle of the phase angle of my voltage. We are effectively throwing away the e to the j omega t part, and we'll see why we get to do that in just a moment. So to get our phasor representation of our voltage, we simply keep the magnitude, keep the phase angle, and throw the rest away. That is how we are going to convert from the time domain into the frequency domain for voltage signals. We're going to do the exact same thing for current signals. So our phasor representation of our current is going to be the magnitude of our current, angle, the phase angle of our current, and we throw the rest away. The only thing that we need to pay explicit attention to is that our time domain signals must be expressed in a cosine form in order for us to do this. So the cosine form of our sinusoidal signals is the basis that all of electrical engineering uses. We're using it because it's the real part of that complex representation. So these signals over here are our frequency domain signals, which we more commonly call phasors. Phasor is just a portmanteau of phase vector. So let's practice really quickly here. So let's say that I had a time domain signal that was 10 cosine 37t plus 106 degrees. What would the phasor representation of this signal be? Yep. Keep the magnitude, keep the phase angle, throw the rest away. 10 angle 106 degrees volts. All right. What if we had 14 sine 6 pi plus 98 degrees volts? What would our phasor representation be? Thank you, yes. Let me move that plus sign over because it's a little wonky. $14 angle 8. Yep, because we convert from sine to cosine by subtracting 90 degrees from our phase angle. So just 14 angle 8 degrees volts. What if we had VC that was 7 cosine 4t plus 10 degrees minus 6 sine 4t volts? I would do this by saying that I have 7 angle 10 minus 6 angle negative 90. Throw that in my calculator. And I get 9.979 with an angle of positive 46.307 degrees. So we definitely don't do the math in the time domain. Cannot make that clear enough. All right, so we have successfully converted our signals from the time domain to the frequency domain. How hard do you think it is to convert from the frequency domain to the time domain? Not hard at all, right? All we need to know is omega. That's the only piece of information that is not explicitly given. So if we were told, for example, that we had a circuit where we had a current, phasor current I was 10 angle 65 degrees at an operating frequency of omega is equal to 5 radians per second, our time domain representation would be 10 cosine 5t plus 65 degrees amps. Magnitude's the same, phase angle's the same. We just got to stick that omega in where it needs to go. That's it. That is how we convert from the frequency domain back to the time domain. Okay. So voltages and currents are pretty easy to go from the time domain to the frequency domain and vice versa. So what I want us to do now is I want us to develop frequency domain relationships for capacitors, inductors, and resistors. We're going to start with resistors first. So let's say that I have a resistor. Actually, let me give this section title. So if I have a generic resistor R, across which I have some voltage V of t and some current I of t. Let's say explicitly that V of t is a sinusoidal voltage, so Vm cosine of omega t plus theta v, and I of t is Im cosine omega t plus theta I. If I want to figure out what my frequency domain relationships are, I'm going to actually use my mixed domain signals. So recognize that these are the real parts of Vm e to the j omega t plus theta v. And our current is the real part of Im e to the j omega t plus theta I. So what is the relationship between voltage and current for a resistor in the time domain? What? Ohm's law, yeah. So we could say that V of t is equal to R times I of t. This is nothing more than Ohm's law. Are we all okay with this? So all I'm going to do is I'm going to substitute in that complex number relationship, okay? So that means I'm going to have Vm e to the j omega t plus theta v is equal to R times Im e to the j omega t plus theta I. Okay. This next step, I'm only going to do this explicitly this one time because we're going to do it so much that it's going to get annoying. I'm going to split these exponentials up. Okay. So e to the j omega t plus theta v could be written as e to the j omega t times e to the j theta v. And I'm going to do the exact same thing for my exponential on the right-hand side. E to the j omega t times e to the j theta I. Now from here, we can see that we have a common factor of e to the j omega t on both sides, which means we just get to throw that part away, which happens to be exactly the reason why we can treat phasors the way that we do, where we just throw that omega t bit away because it's common to everything. Okay. That leaves us with Vm e to the j theta v is equal to r times Im e to the j theta I. So I want to make an observation here, okay? On the left-hand side of my equal sign, I have an exponential form complex number. And on the right-hand side of my equal sign, I have an exponential form complex number. So that means that the magnitude of the thing on the left has to be equal to the magnitude of the thing on the right, and the phase angle of the thing on the left has to be equal to the phase angle of the thing on the right. So we can see that the magnitude of our voltage Vm is just the magnitude of our current times R. We can also see that the phase angle of our voltage, theta V, has to be equal to the phase angle of our current, theta I. So effectively, for a resistor, we don't experience any delay or any phase shift. The current and the voltage are exactly in phase because their phase angles are the same at all points in time. Okay. So Vm e to the j theta v can be written as Vm angle theta v. So going from the exponential form to the polar form. Similarly, on the right-hand side here, we would have R times Im angle theta I. And from our definition of what a phasor is, this is just phasor voltage V is equal to R times phasor current I. So Ohm's law in the frequency domain is exactly the same as Ohm's law in the time domain. Any questions before we hit inductors? So I'm gonna circle the key takeaway stuff here because I'm worried you guys are afraid you might have to do derivations and all this kind of stuff. You don't, that's why I'm doing them, okay? So what I want you to take away from that part right there is that phasor voltage V is equal to R times the phasor current I. And then I also want you to remember the magnitude relationship and the phase angle relationship, because we're going to use those again and again and again. Now let's repeat what we just did, but with an inductor. So what is the derivative-based relationship between inductor current and inductor voltage? So V is equal to L di by dt, right? We learned that a couple of weeks ago. So let's see what shakes out from this using those complex number relationships for voltage and current. So we would have Vm e to the j omega t plus theta v is equal to L times the derivative of Im e to the j omega t plus theta I. That Im is a constant, so we can just move that outside of the derivative. How do I take the derivative of e to the j omega t plus theta v? What's that going to look like? All right, so just as a quick aside here, I feel like I've already talked to you guys about this, but that's okay. The derivative of e to the AT is a e to the AT, right? In this case, a is just j omega. So when I do this derivative, what I'm going to get is j omega L times Im e to the j omega t plus theta I. We have that common factor of e to the j omega t on both sides of our expression again, so I can throw that part away, leaving me with Vm e to the j theta v is equal to j omega L times Im e to the j theta I. All right, so right now we have this in kind of an interesting form, okay? So let me explain what I mean. This part right here is a polar form complex number, or an exponential form complex number. This part right here is also an exponential form complex number. But that part is a rectangular form complex number. So we are multiplying two complex numbers together. And we learned that multiplying complex numbers together is easiest when they are both exponential or polar form complex numbers. So how would I represent j omega L as an exponential form complex number? So let's scroll down here and look at our complex plane. So this is where we have real numbers. This is our axis for imaginary numbers. And just while we're at it, this would be a phase angle of 0 degrees, 90 degrees. Out here would be plus or minus 180 degrees. Down here would be negative 90 degrees. Where is j omega L going to lie on this complex plane? Somewhere up here, right? There is no real part to this complex number. It's only positive and imaginary. So we would have j omega, excuse me, not j omega, we would have something that is omega L units in the positive imaginary direction. So j omega L is just omega L with a phase angle of positive 90 degrees. Okay. So I could rewrite this as omega L times Im e to the j theta I plus 90 degrees. Because if I multiply e to the j theta I times e to the j 90 degrees, I just get to add those arguments of that exponential function together. So from this, we can see that the magnitude of our voltage is equal to omega L times the magnitude of our current. And we can see that the phase angle of our voltage is equal to theta I plus 90 degrees. So what does it mean that theta V is always 90 degrees ahead of theta I? Maybe I phrased that poorly. I'm thinking in terms of leading and lagging, comparing signals, right? So what we have just stumbled into here is that for an inductor, the voltage will always lead the current by exactly 90 degrees, or transversely, the current will always lag the voltage by exactly 90 degrees. You guys are actually going to figure this out in a lab next week. So here's two of the relationships that I expect you to remember for this, because they're going to pop up again and again. Going back to what we have up here, Vm e to the j theta v looks like our phasor voltage V. That will be equal to j omega L times our phasor current I. So that's our frequency domain current voltage relationship for an inductor. Any questions about this one before we move on to our last bit, which is capacitors? All right. I promise I'm like within, I think, 20 minutes or so of being finished talking at you guys, for what it's worth. So here's our capacitor. Our voltage V of t, our current I of t. And we know that our derivative-based relationship is our capacitor current I is equal to C times our derivative of our voltage. This relationship is effectively the exact same thing we just did for inductors, except that we replaced L with C and we swapped the position of I and V. So instead of deriving all of this stuff again, I'm literally going to do just that, right? So what we'll find is that I phasor is equal to j omega C times V phasor. So that's one of our relationships. We will have IM will be equal to omega C times Vm. That's our magnitude relationship. And then we will have theta I is equal to theta V plus 90 degrees, which is our phase angle relationship. And once again, I got these three relationships literally by looking at these three inductor relationships and swapping everywhere I have a voltage thing, I replace it with a current and vice versa, so forth. Okay. All right. So we now have our current and voltage relationships for resistors, capacitors, and inductors. So now I want to talk about the concept of impedance. So when we had a DC circuit, we saw that if we excited our DC circuit and we measured the voltage across the terminals of the network and the current flowing into the network, that our resistance was simply the ratio of V over I. Once again, our fundamental definition for Ohm's law. This was third day of class stuff. If we have an AC circuit in the frequency domain, so if we have a network and we sinusoidally excite it, if we measure the phasor voltage across the terminals of the network and measure the phasor current flowing into the network, we will define impedance Z to be the ratio of the phasor voltage to the phasor current. So impedance plays the role that resistance did in DC circuits, okay? So impedance is by definition just the ratio of our phasor voltage to our phasor current. Well, in the frequency domain, our voltages and currents are complex numbers, which means our impedance must also be a complex number. Okay? So Z is the ratio of our phasor voltage to our phasor current. So in polar form, this is going to look like Vm angle theta V divided by Im angle theta I, which is just the magnitude of our voltage divided by the magnitude of our current with a phase angle of theta V minus theta I, or the magnitude of our impedance with a phase angle, which is the phase angle of our impedance. Okay. So that is our polar form representation. In rectangular form, our impedance will have some real part, right? So we'll have the real part of Z plus J times the imaginary part of Z. Well, the real part of Z is resistance. Literally just the resistance that we've been dealing with. The imaginary part, we give the symbol X, which is for reactance. Okay? So this is resistance. This is reactance. And this is just our rectangular form representation of our impedance. So what I want us to do now is figure out what the impedance of a resistor is. So if we have just a resistor by itself, what is phasor voltage V divided by phasor current I? Look at your notes from 10 minutes ago. So if I'm not mistaken, we had V is equal to I times R. And I want V divided by I, which gives us R. Yes. So the impedance of a resistor is just the resistor value itself. More formally in rectangular form, this would look like R plus J0. And more formally in polar form, this is R with a phase angle of 0. What are the units of resistance? Ohms. So all of these are measured in ohms. Okay. So for a resistor, nothing changes in the frequency domain. We have a resistor, we keep a resistor. What would the impedance of an inductor look like? So go back to your notes from a couple of minutes ago and divide both sides by I. J omega L. More formally, 0 plus J omega L. In polar form, that would be omega L angle positive 90 degrees. Let's look at the units really quickly. So omega is measured in per seconds. and L is henries, where a henry is a volt second per ampere. So volt second per ampere. Seconds and multiplied by per seconds cancel each other out. So what's a volt per amp? It's an ohm. So the impedance of an inductance is just J omega L measured in ohms. Let's look at a capacitance. So what is the ratio of phasor V over phasor I going to be for a capacitor? 1 over J omega C. Which in rectangular form is going to look like 0 minus J divided by omega C. 1 over J is the same thing as negative J in the numerator. Look back at that table of all of the different versions of J that we did at the beginning of our complex number review. And so we can also say in polar form that this is 1 over omega C with an angle of negative 90 degrees. So we would have 1 over per second multiplied by something in farads, where a farad is an amp second per volt. Seconds times per seconds, we get rid of that. What is 1 over an amp per volt? Volt per amp, which is an ohm. So all of these impedances are measured in ohms. What is a side effect of that? We get to treat everything like it's a resistor. There are no special rules for combining inductors, capacitors, and all that kind of jazz anymore. Everything combines like resistance. It's just now we have imaginary numbers involved. So let's take this concept of impedance and let's go way back to what we had way at the top. So there's not a whole heck of a lot of room here, but we don't need a whole heck of a lot of room. I want to convert this circuit. Are you raising your hand or you're stretching? Okay. I want to convert this circuit from the time domain into the frequency domain. Okay. So what is the phasor representation of my voltage going to be here? Twelve angle 10. All right. What is the phasor representation or the frequency domain representation of my resistor going to be? Just the resistor. What's the impedance of my capacitor going to look like? So 1 over J omega C, where omega is 5 and C is 5 millifarads, right? So 1 over J times 5 times 5 times 10 to the minus 3. I get negative J 40 ohms. How would I find this current phasor IS? So I think IS would be V phasor over 10 ohms plus V phasor over J 40 ohms, and we know what that V phasor thing is, right? So I'm going to do 12 angle 10 divided by 10 plus 12 angle 10 divided by 40J And I get. Did I do something wrong here? I got a different phase angle than I was expecting. What mistake did I make? Oh, I should have a negative sign here. That's the problem. Thank you. 12 angle 10 over 10 plus 12 angle 10 over negative 40i. And I get that exact same 1.234 angle 24 degrees and change that I got earlier. So working in the frequency domain, using phasor relationships for our voltages and currents and impedances for our resistors, capacitors, and inductors, effectively allows us to just use the same DC circuit analysis techniques that we learned at the very beginning of this class to analyze any steady state sinusoidal circuit. So we have come full circle in this class, okay? By using complex numbers, we can make any hard looking AC circuit effectively into a DC circuit. We just have to deal with complex numbers. And so that's all we're going to do for the next several class meetings, okay? So before we meet on Monday, what topics from exam 1 do you guys need review on? Because that's all this next couple of days is. How do you feel about superposition? How do you feel about current division? How do you feel about voltage division? Thevenin and Norton's equivalent circuits. Which of those things do you need review on? And then we'll spend the next couple of days just doing that in the context of AC circuit analysis. Voltage and current division, okay. Anybody else have Hojun? Superposition. Anybody else? Thevenin and Norton equivalent circuits as well, apparently. Okay. All right. So, like I said, we're just going to spend the next couple of days actually reviewing exam 1 material just in the context of this stuff. All right. I am done ranting for today. Thank you guys for your patience and allowing me to talk so much about all of this ridiculous math.